Hello and welcome back to Corporate Finance. We will continue our discussion in Chapter 4. Chapter 4 deals with time value of money, valuing cash flow streams. In this video, we will discuss perpetuities and annuities. The formulas we have developed so far allows us to compute the present or future value of any cash flow stream. So in this video, again, we will discuss two types of cash flow streams, which are perpetuities and annuities. A perpetuity is a stream of equal cash flows that occur at regular intervals and last forever. Again, perpetuities is a stream of, or are a stream of equal cash flow involving a series of cash flows that continue indefinitely into the future. In perpetuities, the cash flows occurs at regular intervals and are considered perpetual, meaning they have no fixed end date. The most common example of a perpetuity is a constant, unending stream of regular payments. The valuation of perpetuities is often calculated using the perpetuity formula, which involves dividing the cash flow by the discount rate. Here you see the timeline for a perpetuity. The first cash flow does not occur immediately. It arrives at the end of the first period, as you see in the timeline. Using the formula for present value, the present value of a perpetuity with payment C and interest rate R is given by what you see here in this formula. So PV equals start fraction C over left parentheses 1 plus R right parentheses, right? That's what you see here. Plus C over 1 plus R in parentheses to the second power plus C over 1 plus R in parentheses to the third power. So notice that all cash flows are the same. Also, the cash flow starts at time 1. There is no cash flow at time 0. Let's derive a shortcut by creating our own perpetuity. Suppose you can invest $100 in a bank account, paying 5% interest per year forever. At the end of the year, you'll have $105 in the bank. Your original $100 plus $5 in interest. Suppose you withdraw the $5 and reinvest the $100 for another year. By doing this year after year, you can withdraw $5 every year in perpetuity. So here in the timeline, you see from left to right, at 0, you have the negative $100. And at 1, you have $105 minus $100 gives you $5. And then at 2, you have the $105 minus the $100 will give you $5. And then at 3, you have $105 minus the $100, which will give you $5. So you see this arrow. The arrow points from the negative $100, the value of each year, to $105 value of the next consecutive year. To generalize, suppose we invest an amount P at an interest rate R. Every year we can withdraw the interest we earn, C equal R times P, leaving P in the bank. Because the cost to create the perpetuity is the investment of principal, P, the value of receiving C in perpetuity is the upfront cost, P. Rearranging C equal R times P to solve for P, we have P equal C over R. Here you have the present value of a perpetuity. The present value, then C in perpetuity in parentheses equals C over R. So by depositing the amount C over R today, we can withdraw interest of C over R times R equals C each period in perpetuity. And here I have this table or notations for the letters again that you learned in chapter 3 and chapter 4. So when I just say the letters, you should know what it means. C is cash flow. C, then you N, the lowercase n is cash flow at date N. FV is future value. G is growth rate. P is the principal or deposit. PV is present value. Lowercase r is the interest rate or the rate of return. Here's a problem. You want to endow an annual graduation party at your alma mater. You want the event to be memorable. So you budget $30,000 per year forever for the party. If the university earns 8% per year on its investment, and if the first party is in 1 year's time, how much will you need to donate to endow the party? How do we plan this? Here you see the timeline of the cash flow you want to provide is $30,000 for each year. Now, this is a standard perpetuity of $30,000 per year. The funding you would need to give the university in perpetuity is the present value of this cash flow stream. To execute, you use the formula for perpetuity, which is present value equal cash over rate or interest rate. So you have 30,000 divided by 0.08 equal $375,000 today. So let's evaluate. So if you donate $375,000 today, and if the university invests it at 8% per year forever, then the graduates will have $30,000 every year to fund their graduation party. Here's another problem. Endowing a perpetuity. Endowing a perpetuity example. You just won the lottery and you want to endow a professorship at your alma mater. You are willing to donate $4 million of your winnings for this purpose. If the university earns 5% per year on its investments and the professor will be receiving her first payment in 1 year, how much will the endowment pay her each year? Here you see the timeline for the cash flow which you want to provide. Now, this is a standard perpetuity. The amount she can withdraw each year and keep the principal intact is the cash flow when solving equation 4.4. And we discussed that formula before, but here you see the formula for the perpetuity. Present value equals C over R, so C is equal to PV, present value times the interest. So C is equal to $4 million times 0.05, which will give you $200,000. So if you donate the $4 million today, and if the university invested at 5% per year forever, then the chosen professor will receive $200,000 every year. Annuities. What is an annuity? An annuity is a stream consisting of a fixed number of equal cash flows paid at regular interval. Again, annuities are a stream that involves a series of periodic payments made or received over time. Now, these payments can occur at regular intervals, such as monthly, quarterly, or annually. Okay? The difference between an annuity and a perpetuity is that an annuity ends after some fixed number of payments. Present value of an annuity. Note that just as a perpetuity, we assume the first payment takes place one period from today. And here you see the formula. To find a simpler formula, use the same approach as we did with a perpetuity. Create your own annuity. With an initial $100 investment at 5% interest, you can create a 20-year annuity of $5 per year. Plus, you will receive an extra $100 when you close the account at the end of 20 years. And here you see the timeline. So at 0, you have the negative $100. Then at 1, you have the $105 minus $100, which leaves you with 5. Then at 2, you see the $105 minus $100, which leaves you again with 5. And then the consecutive years, at year 20, you have the $105 plus $5 plus $100. You see that there's an arrow that points from the negative $100 value of each year to $105 value of the next consecutive year. The law of one price. The law of one price tells us that because it only took an initial investment of $100 to create the cash flows on the timeline, the present value of these cash flow is $100. So that's $100 equal the present value. Then you have the 20 minus year annuity of $5 per year in parentheses, plus the present value. And then in parentheses, you have the $100 in 20 years. So with rearranging, you have the PV, 20 minus year annuity of $5 per year, equal $100 minus PV. Then you have the $100 in 20 years in parentheses, equal 100 minus 100 over 1.05 to the 20th power, meaning that's the 20 years, equal $100 minus $37.69. And that is a balance of $62.31. We usually want to know the present value as a function of C, R, and N. Since C can be written as $100, and then you have the 0.05 in parentheses equal $5, we can further rearrange. And here you see the formula for that. So the first line reads the PV 20 minus year annuity of $5 per year in parentheses equals the fraction of $5 by 0.05 minus the fraction with numerator $5 by 0.05 and denominator 1.05 raised to the 20 power, which equals the fraction of $5 by 0.05 times 1 minus the fraction with numerator 1 by denominator 1.05 raised to the 20 power. And in the last part of the equation, you have $5 is marked as C and 20 is marked as the uppercase N. The second line is equal $5 times the fraction 1 by 0.05 times 1 minus the fraction with numerator 1 by denominator 1.05 raised to the 20th power, where 0.05 and 1.05 raised to the 20th power are marked as R. So in general, you have PV which is left parentheses annuity of C for N periods with interest rate R, right parentheses, equals C times start fraction 1 over R, N fraction left parentheses 1 minus start fraction 1 over left parentheses 1 plus R, right parentheses, superscript, and it's where we are, baseline N fraction right parentheses. So all I'm saying is the C times 1 over R, and in parentheses, you have the 1 minus 1 over, in parentheses, 1 plus R, then you have N. Okay, present value of a lottery prize annuity. You are a lucky winner of a $30 million state lottery. You can take your prize money either as a 30 payment of $1 million per year starting today, or B, $15 million paid today. If the interest rate is 8%, which option should you choose? Here with option A provides $30 million in prize money, but paid over time. To evaluate it correctly, we must convert it to a present value. And here you see the timeline. Starting at 0, 1 million, 1, 2, 3, and until 29, you have the $1 million. So because the first payment starts today, the last payment will occur in 29 years for a total of 30 payments. The $1 million at date 0 is already stated in present value terms, but we need to compute the present value of the remaining payments. Fortunately, this case looks like a 29 annuity of $1 million per year, so we can use the annuity formula. To execute, we use the annuity formula, which is present value. Then you have 29 minus year of 1 million at 8% annual interest rate in parentheses. And to calculate that, you see, I'm just going to read the last line, which is equal to 11.16 million today. Thus, the total present value of the cash flows is 1 million plus 11.16 million equal 12.16 million. With option B, the 15 million upfront is more valuable, even though the total amount of money paid is half that of option A. Financial calculators or Excel can handle annuities easily. You just enter the cash flow in the annuity as the PMT on your calculator. And if you have a financial calculator, this is how it would show, or how it should display. So it shows the two rows given. Now, both the financial calculator and Excel will give you the PV of the 29 payments, which is 11,158,406, or 11.16 million, to which you must add the first payment of 1 million, just as shown. To evaluate, the reason for the difference is the time value of money. If you have the 15 million today, you can use 1 million immediately and invest the remaining 14 million at an 8% interest rate. This strategy will give you 14 million times 8% equal 1.12 million per year in perpetuity. Alternatively, you can spend 15 million minus 11.16 million, which will give you 3.84 million today, and invest the remaining 11.16 million, which will still allow you to withdraw 1 million each year for the next 29 years before your account is depleted. Present value of an annuity starting today. Present value of an annuity starting today. Here's the problem. Your parents have made you an offer you can't refuse. They're planning to give you a part of your inheritance early. They've given you a choice. They'll pay you $10,000 per year for 7 years, beginning today, or they'll give you their 2018 BMW M5 convertible, which you can sell for $61,000, guaranteed today. If you can earn 7% annual on your investment, which should you choose? Option A provides $10,000 paid over time. To evaluate correctly, we must convert it to the present value. And here you see the timeline. Beginning today, date 0, $10,000. 1, 2, 3, 4, 5, 6, you see the $10,000 at each date. To plan, the $10,000 at date 0 is already stated in present value terms, but we need to compute the present value of the remaining payments. Fortunately, this case looks like a 6-year annuity of $10,000 per year, so we can use the annuity formula. So from the formula of an annuity, you have the present value, then you have the 6 minus year annuity in parentheses equal 10,000 times 1 over 0.07. And then you have 1 minus 1 over 1.07 to the 6th power in parentheses. So the present value, 6 minus a year annuity in parentheses, is equal to $47,665. So the present value, the total present value of the cash flow is $10,000 plus $47,665. And this you see in the timeline, which will give you the $10,000 plus the $47,665, which will give you $57,665. Here you see a display of the financial calculator. So you would enter the cash flow in the annuity as PMT, which is the 10,000. With the Excel, you would input present value and then put in parentheses rate, NPER, payment, and then future value, which will give you the present value. You have 0.076, then 10,000, then 0 in parentheses. Lucky you, even you don't want to keep it, even if you don't want to keep it, the fact that you can sell it for more than the annuity is worth means you're better off taking the BMW. Future value of an annuity. Here you see the future value formula, which is a future value annuity in parentheses equal PV times 1 plus R in parentheses to the N power. I'm just going to leave that for just a second for you to look over it. Retirement savings plan annuity. Problem: Ellen is a 35-year-old and she has decided it is time to plan seriously for her retirement. At the end of each year until she's 65, she will save $10,000 in retirement account. If the account earns 10% per year, how much will Ellen have in her account at age 65? As always, we begin with a timeline. In this case, it is helpful to keep track of both the dates and Ellen's age. So here you see the timeline starting at 35 and ending at her retirement age of 65 at $10,000 every year. Ellen's savings plan looks like an annuity of $10,000 per year for 30 years. It is easy to become confused when you just look at age rather than at both dates and age. A common error is to think that there are only 65 minus 36 equal 29 payments. Writing down both dates and age avoids this problem. To determine the amount Ellen will have in her account at age 65, we'll need to compute the future value of this annuity. And here you see a display of the financial calculator. And then also at the bottom, you see how you would input the information into an Excel spreadsheet for computing it. So it appears that at age 65, Ellen will have $1.645 million in her account. So by investing, by investing $10,000 per year for 30 years, a total of $300, and earning interest on those investments, the compounding will allow Ellen to retire with $1.64 million. That if she starts at the age of 35. Retirement savings plan annuity. Adam is 25 years old, and he has decided it is time to plan seriously for his retirement. He will save $10,000 in a retirement account at the end of each year until he is 45. At that time, he will stop paying into the account, though he does not plan to retire until he is 65. If the account earns 10% per year, how much will Adam have saved at age 65? As always, we begin with the timeline. You see the timeline here. In this case, it is helpful to keep track of both the dates and Adam's age. Starting at age 25, and 65. What would it be if he invested until 65? So Adam's savings plan looks like an annuity of $10,000 per year for 20 years. The money will then remain in the account until Adam is 65 minus 20 more years. To determine the amount Adam will have in the bank at age 45, we'll need to compute the future value of this annuity. Then we'll compound the future value into the future 20 more years to see how much he'll have at 65. To execute, you see here a display of the financial calculator, and at the bottom you see the Excel formula that you would use in an Excel spreadsheet. So to execute, face future value at age 45 equal $10,000 times 1.10 to the 20th power minus 1 in parentheses equal $572,750 at age 45. If he had continued to age 65, you see that the future value at age 65 is equal to $3,853,175. So by evaluating, we see here that for Adam, by investing $10,000 per year for 20 years, which is a total of $200,000, and earning interest rate on those investments, the compounding will allow him to retire with $3.85 million. Even though he invested for 10 fewer years and $100,000 less than Ellen did, Adam will end up with more than twice as much money because he's starting his retirement plan 10 years earlier than Ellen will. And this is the end of this video where we talked about perpetuities and annuities.